Welcome to this IHS Global Spec Alternative and Renewable Energy online event. There is a rapidly increasing demand for local renewable energy generation. Any new source of local clean energy is of critical concern. Water flows big and fast in millions of places around the world, and new hydrokinetic technology, along with other new enabling technologies, makes micro hydropower generation in these places now feasible. Before introducing our speaker, we'd like to invite you to submit questions at any point during this presentation by using the Submit Question button at the base of this video console. Also, some of the presentations you will see today include detailed information, so we would encourage you to click the Download PPT button so that you can follow along with your own copy of the PowerPoint slides. Burt Hamner is CEO and founder of Hydrovolts Incorporated of Seattle. Hydrovolts make small hydrokinetic turbines that generate clean renewable power in drinking water from irrigation canals, waterfalls, and other constructed water channels. Burt graduated with honors from Harvard, studying marine biology, and obtained a master's degree in business administration and marine affairs from the University of Washington in Seattle. Burt, welcome to today's event.
Thank you, Jim. I'm Burt Hamner. I'm the CEO and founder of Hydrovolts in Seattle, Washington. Our company makes innovative new hydrokinetic turbines to generate renewable energy from water currents. And today I'm going to talk about alternative and renewable energy in the hydropower space for this Global Spec 2013 online seminar. And the focus is on practical alternative hydropower, not the more dreamy stuff. So our agenda for today is to cover, first of all, the difference between traditional and alternative hydropower. Then we'll talk about wave and tidal energy, rivers and streams as sources, then canals, water canals. We'll talk about industrial water systems as a source, and then finally about nano hydro, very small hydro, which has gotten very valuable. And then finally as well about interconnecting, because it's one thing to make power, you still got to plug it into something, and that's not as easy as one might think. So let me begin by talking about alternative and traditional hydropower. So traditional hydropower is based on the height or the pressure of water. So we have a dam and it has altitude. The higher the water is compared to the outlet, the more energy can be extracted. So you need vertical drops in containment. And dams and pipes are the obvious big solution, big vertical pipes. And as a consequence of the need to impound water, almost all normal traditional hydro requires a lot of civil construction. There's a lot of engineering and permitting and site placement and environmental issues, etc. As a consequence, very small hydro is possible, but it's typically not done much for the very simple reason is you can't make enough electricity with very small hydro systems to pay off all the infrastructure necessary to get it in the first place. Also, very small hydro sites tend to be placed in things like rivers and sharp hillsides where bad flooding typically washes them away eventually. So alternative hydro that we're going to talk about today is based on water velocity and not pressure. So this is about the horizontal speed or the vertical speed of the water moving. And so in horizontal velocity, it's just like wind. So an underwater hydrokinetic turbine is just like an underwater wind turbine. It's driven by the fluid. In wave energy, it's the movement up and down of the water that causes the hydrokinetic power. And in the physics of hydrokinetics is a very important factor, which is that the power increases with the cube of the velocity of the water. So if you double the speed, you get 8 times as much energy. So if we go from 2 meters per second or 4 knots to 3 meters per second, we don't get 50% more power, we get 6 times more power roughly. So speed is everything in hydrokinetic alternative energy, all right? And you really need about 4 knots or 2 meters a second to get power that's useful. That's about a fast walking speed. So if you see water and you're walking fast to keep up with it, there's energy there. But if you're just ambling along, there's not a lot of power. So we got involved in this business when we started studying tidal power for one of the utilities here in Washington State. And during 2007, I directed a team of 8 engineering companies to look at Tacoma Narrows, which you see in this video. The Narrows is in the city of Tacoma, Washington, separating the northern and southern parts of Puget Sound. This channel is about 8 kilometers long and 1 kilometer wide. It gets up to 6 knots, so there's a lot of energy there. The red color you see there in the video shows the fast currents. And as you can see, there are places where it's fast and big, but you'll notice it's very intermittent and it's extremely turbulent. And that's an indicator of what are the problems with tidal power in general, and that even though it's predictable, it's chaotic, and also it's just difficult to site things in just the right place because of the turbulence. And as a consequence of the lack of speed in most places, plus these problems, tidal power in the USA is not practical. It doesn't have much of a future because only places like the Bay of Fundy and remote Alaska have got water velocities fast enough to really drive a turbine to make it practical. The other problem is that the capital expenditure and O&M costs, the maintenance costs of these things, are just insane. Our own study showed it would bring power to shore, if we could build it, at around 35 cents a kilowatt, whereas right now natural gas can be used to generate power at about 3 to 4 cents a kilowatt. There is no competitive advantage here from tidal power. Around the world, Scotland is actually the place with the best sources for tidal energy, and they're very active on it. But that's really it. There's not a lot of other sites. Wave power has limited potential. Waves need to be big and strong and steady to generate the kind of power that's necessary. And here you see in this video a site off of Portugal with a machine called the Pelamis, also known as the wave snake. And you can see how it undulates in these big waves, and it generates power from compression of fluid inside the machine, driving a hydraulic powered turbine. But it's a very big machine, it's expensive, and it's way offshore. And again, the problem here is that there aren't very many places this really works. Not only do you have to have a good wave resource, you have to have it accessible from shore, and also you got to run a lot of cable. So it's very expensive. Underwater cable for a wave energy system costs $1 million a mile. And if you're 10 miles offshore with a big array, you're running maybe 40, 50 miles of cable, and you're all of a sudden looking at a $16 million cost just for the wire. So wave power's really also got a limited future. Rivers and streams have always been a great interest to people, and here we see some pictures of 4 different turbines built in the past to put into rivers in different places. And none of them last very long because, A, the power is not very high, it's not worth it. Second, they are almost always defeated by floating debris. So in rivers and streams, the problem is nature rocks. Nature puts floods and trees and animals and regulatory agencies in your way. It's even hard to get into the river and hold on to something because it's not a natural environment. And as a consequence, we don't see much of a future for alternative hydropower in rivers and streams. So if I've taken away all the impractical places, where are the practical places to do this? Well, the short answer is in big artificial water systems such as canals, used for irrigation and water supply, and in big industrial water treatment facilities like you see in this picture here, and also in a variety of other water diversion structures. And they all share a couple things in common. The water is managed and owned by engineers, so it's predictable. Second, it's filtered. They keep the trees, coyotes, cars, and teenagers out of it as much as they possibly can. And third, because it's an artificial system, there's usually no environmental issue there, or if it is, there's a very minor one. These are not natural habitats, and as a consequence, they don't have to go through the kind of environmental problems that others do. So our solution to tap this resource is our new waterfall and canal turbines at Hydrovolts. We've invented a snap-on waterfall turbine that hangs on the edge of a concrete wall and captures that water falling down. It's portable and can be installed quickly. And we have a canal turbine that installs in a typical irrigation canal and also makes power. They can make power for 3 to 4 homes per turbine. So if you have a bunch of machines, you can power a lot more homes. This solution is really important because it means that we can put these things in quickly. These are concrete ditches or concrete environments, so you can walk up and hang stuff in there really fast. We can install a turbine in a day. We can do hydropower in a day. Whoever heard of a hydropower system being installed in a day? Second, it doesn't take much in the way of permitting because these are owned by big organizations and they can handle all the permits themselves, if a permit's needed at all. And it's also modular and scalable in that if you have a bigger canal, you can attach turbines to each other or you can put them one after another down the length of the system. And the value proposition, because it's simple and fast, is a lot better than many other resources. So we're aiming in our technology to deliver a value of about 4 to 6 cents a kilowatt for power output, and giving the customer a return on their investment of about 6 to 7 years in a market where electricity costs 11 cents a kilowatt. 11 cents is the U.S. national average. It's a lot higher in New England and California, and it's a lot less in places like North Dakota with a lot of coal. So the value of the technology depends where you are. And in our case, we're looking at markets much beyond the United States where power is a lot more expensive, such as Europe, or where it's subsidized in other areas such as Japan. So what we've done in Hydrovolts is we have taken 3 types of technologies and a key business model. First of all, we're using a cross-axis, what we call switchblade hydrokinetic rotor that allows us to put different types of rotors on the same shaft. So it's adaptable to a lot of different sites. The second thing we're using is low-speed permanent magnet generators that don't require a fast transmission to make them run. And that eliminates the need for a gearbox and also for the need for speed controllers. So all of a sudden, the power generation side of it just got a lot cheaper and more reliable. Third, we're using new types of inverters that are coming from small wind and solar so we can connect cheaper than we could in the past. Those 3 things are enabling technologies that make micro hydropower suddenly a lot more effective. These technologies were not available in the 20th century, but now they are. We combine those 3 enabling technologies with our sector focus, which is artificial, man-made, big water systems only. We're not touching rivers. We're not touching the ocean. The moment you touch those things, they're like tar babies. They suck you in and they get all, and you spend all your money. Artificial systems makes a business model that works for this technology. So here's a picture of our switchblade turbine showing 4 different rotor sets on it. We have in the upper left the high-speed Darius blades that are suitable for laminar, fast flows like you'd find in an outfall from a dam or in a discharge in a big channel. We have a Savonius design that's more suitable for slower speeds and more turbulence. This rotor is designed for waterfalls and spillways. It's a barrel rotor. And then down and below we have the flip wing rotor, which is my own invention, and that is designed to be useful in all these situations. So again, coming back to the key part of the business model, one machine now can adapt to a lot of different sites. So we don't have one turbine, we have a 4-way switchblade turbine. The flip wing rotor is really quite unusual. What we have here is metal plates that are attached by a shaft on the outside of the perimeter. So in this video, you're looking end on at the turbine. And so the plates are just long enough to reach that center shaft, which stops the blade at that point, and the water pushes it over the top and it flips open, as you can see. It's easy to make it. It's very hard to foul it. It works in any velocity of current, and it can accommodate any size of blades. So we're very excited about this as a new rotor concept. It's not as efficient as other rotors are, but it's a lot cheaper to make. And what we're really talking about is total cost, not efficiency. So if it's cheaper to make, but a little less efficient, that still is a good deal. So we took that rotor and put it on our small canal turbine, and here you see it in the process. It's now floating away in a canal here in Washington State. That particular machine you see in the video is about 4 feet long. It's able to charge up about 48 volts of power, charge a couple car batteries. It's held in place with just 2 ropes, and the power line goes up one of the ropes, and it can be put in place with 2 people. So it can also be taken out. And we let that run in this canal for a full month in the middle of bad weather with a lot of crap in the water, and it didn't foul. The same machine was tested later by the U.S. Navy, and here you see it being operated by the Navy in one of their facilities near Washington, D.C. This machine is about 6 feet long and about 2 feet in diameter. It's able to produce about 500 watts of power, 24 volts at 24 amps. This is enough to power pumps and irrigation systems and provide backup and emergency power. And it's very interesting to the Department of Defense, which needs remote power in the field. We made a much bigger system, and we've put it into a canal in Northern California called at the Butte Water District north of Sacramento. This machine makes about 8 kilowatts. Again, it's held in place with 2 chains. It sits on the floor of the canal, and they can be installed one after another down the canal, and we can chain them together and make more power. And that's really the secret of what we're after with the canal turbines. It's like the world is covered with highways of water, and we've invented the first car. There they are, those long roads, and we can put one machine after another. Then they're all identical, so we can mass produce them. And around the world, there's a lot of canal systems. In the western United States, over 500,000 miles of canals in total. The Bureau of Reclamation, our state agency from the Department of Interior, that one agency operates 50,000 miles of canals. Other regions of the world with huge systems are South Africa, Southern South America, Southeast Australia, India, Pakistan, Afghanistan area, and interestingly, not only Europe, but also Central Asia, the Uzbekistans, the Turkmenistans, vast areas of scrub with big populations that need food, and so they're putting in huge canal systems to irrigate the land. So there's a global opportunity for one set of machines to expand all over the planet. We started finding waterfalls in the canals too, but then we found waterfalls in big water treatment facilities. And we took our small turbine with a barrel rotor on it and hung it in the waterfall, and son of a gun, it worked just fine. So we've developed a new design for waterfall turbines targeting big industrial water facilities. These would be plants that typically have flows greater than 5 million gallons a day, which is a town of about 10,000 people, or a big factory with a big flow. And these machines are able to generate power that is all used right inside the plant. They don't send it out to the grid. They already use so much energy, they just suck up everything from this turbine, and it saves them money. They don't buy as much outside power. So we started with a proof of concept, and then we built a shop unit to test it out, and have got a new design now that's being installed in Northern California, and the new machine will make about 15 kilowatts of power. We're very excited about this because the global water treatment industry is very well organized, and we've already had contact with several very big multinational engineering companies that want to introduce this technology into their customer base. They service all these big water plants. Because of the uniqueness of our technology approach, but also our business model, Hydrovolts has been recognized by some very distinguished organizations. We've won a number of contests that are judged by venture capitalists and industry experts, such as the Clean Tech Open and Imagine H2O. The Launch.org group has awarded us. And we're very proud of that because these are venture capital people and others with a lot of business experience. They see the technology, they get it, but they really like the business model because they understand that it's got the potential to really grow big very quickly. We're not, of course, the only people making new hydropower. There's a variety of other developers out there, and in this picture here, you can see some of them. There's folks that have got turbines that fit into big discharge pipes, and ones that are for low head weirs, one that looks like a big conveyor belt, and others that are suspended from rafts or fit in the outfalls of pipes, or that look like big screws. The entrepreneurs developing these typically are focused on their technology only, and they lack the flexibility that Hydrovolts has of using different types of rotors on the same machine, so they fit a lot bigger number of sites. And again, some of these folks are pursuing sites that are really quite challenging, where they've got to do a lot of site construction. So the cost is high, even though the power output is low. I'm going to start finishing up here by talking about nanohydro. Nanohydro means making an extremely small amount of power from the water. Why? Because you don't want to generate power for your house. You want to run data collecting sensors. So a company from Israel called Hydrospin has got a new turbine that fits inside a big water pipe, and it's used to measure pressure differences between different places in the pipe so they can tell if they have leaks. And the leaks are very expensive, of course. And their turbine makes enough power to measure the pressure and make a phone call and transmit the data to a central system. We're even looking at the little tiny turbines that are used in hands-free urinals and toilets. So here you see in the center, the Toto toilet makes a microturbine that powers that little flashing light that flushes the toilet or washes the sink out for you when you wave your hands in front of it. It makes just a little power, but so does a USB port for your cell phone. And so we see a very exciting future actually for nanopower generating power to run sensors and then connecting to cell phones so now you can talk to your plumbing. Finally, we'll be talking a little bit here about interconnection. Interconnection has turned out to be a big surprise to me personally because I thought that this was a solved problem, and it turns out it's not. Connecting to something that is grid tied is quite different than connecting to something that's a standalone microgrid. Microgrids have to have their own power management system, and so does the equipment in them. If they're not tied to the grid, a whole bunch of other electrical stuff's got to be done. So off-grid, we're talking really about microgrids, such as homes and villages and farms, not attached to any central system. And the key thing about microgrids, and this is very important for the future of distributed energy, microgrids have to deliver very clean quality power because so many people are using cell phones and laptops. And bad electricity quality with lots of voltage spikes and transients and other bad things in the electricity, like dirty water almost as the analogy, it kills electrical equipment. It burns out motors, it burns out batteries, it burns out phones. So regulating the power created by a source like a turbine is very important. You want to deliver clean, smooth power to your machinery. And that means that you have to have something between the turbine or the wind turbine or the solar system and the hardware. And that's been a new development in what we call integrated power systems with battery backup, which enable you to take a variety of sources, wind, solar, hydro, generators, biomass, plug them all into one box. And out of that box, you get nice, clean power. You've got to have the box, though, and it turns out it's not as easy as people used to think. I certainly was a surprise. So it's possible now to do this because we have very fast signal processing chips. And this is just simply an evolution of computer hardware. Now we can process that electrical signal so fast that the machinery doesn't know that there's been an interruption in a source of something. So now computers are the next thing that's making micro and alternative hydropower possible. Now you can connect it much more effectively. What do we see on the horizon for micro and alternative hydropower? Well, we see regional demo projects, and we're involved with those. We have a request from the government of India to do a demo there now. We see international power generation projects in sites that don't have as many big bureaucratic obstacles as the United States does, for example. It's a lot easier to get a big project into a developing country that doesn't have quite as many lawyers as America does. We see some agencies doing resource and facility assessments. So, for example, the federal government's looking at some regions around the country to say, where can we do this new hydro? Let's map it. And some big water companies are looking at their facilities and saying, where can we do new hydro here? And we're helping them as well. We also see some along the long term that the canals and the plumbing systems themselves will be evolved to take advantage of the new hydro. Canals have always typically been made wide and slow because erosion is bad for them. But we like fast water. Now, in a world where all the canals are getting lined with concrete in order to eliminate seepage to stop the water loss, why not make the canal narrow and fast and save money on concrete too? Well, several engineering companies have come to us with exactly that proposal because that's going to change the way people think about canals as a whole. It's a change in the infrastructure paradigm. And because this is a global world, we see a lot of international collaboration going on around this space. The biggest engineering companies and the biggest water companies, they're global now. So what they can do in Washington State or in the United States, they can transfer to Africa or South America. And they can take this knowledge and move it out quickly to the rest of the world. So they're very excited about that because they get to be thought leaders. So the impact of this new alternative hydropower is very exciting. First of all, there's going to be new energy in a lot of places. We're going to be able to generate new renewable clean power in millions of sites where you couldn't do it before because now we have these enabling technologies. It'll also make something very exciting possible, which is to irrigate more land. We may be able to actually increase food production globally with the use of this hardware because now we can pump water out of a canal and irrigate the land on the side without having electricity at all. We can use the turbine as a pump. It'll also change the way the water systems are designed, as I said. And then finally, it's going to make a lot of new jobs. This is big machinery. You see the turbines in these pictures. This is like making small cars or big agricultural equipment. This is going to create manufacturing jobs, which is very exciting. So Hydrovolts is excited to be changing the water energy game. We can now make micro hydropower possible when it wasn't before, because we can use enabling technologies and a better business model that stays out of the very expensive natural environment. We can change the way water is moved from one place to another, because now you can design the infrastructure to take advantage of turbines that you didn't have before, and that'll change the way they pour concrete. And finally, it'll just make a lot of new things happen. At the bottom of the pyramid, where there's a billion people without electricity, even a little bit of power can do a lot. With cell phones and LED lights, now you can both educate and communicate and stay awake at night with very little energy. So a small turbine can make a big difference to a lot of people. So we're excited about being part of this global spec event and sharing this information with everybody. And I'm looking forward to your questions. Jim, thanks very much.
Burt, thank you so much for that informative presentation. And it looks like we do have a few questions from the attendees, so let's get right to them. The first one asks, how does taking energy out of the water in a canal affect the flow? And does this slow it down, and do you get less water?
If the canal is totally flat, absolutely, because you're putting an obstacle in the way of the water flowing. So the key thing in a canal is it always has a slope, because that's how the water gets from one end to the other. So the key is that the first turbine in the canal has to be far enough below the entrance that it doesn't block the flow into the canal. Once the water's in the canal, if you put more turbines in, each one acts like a little dam and the water level in the canal goes up, but the throughput remains the same. What goes in this end has got to come out that end at the same rate, otherwise it spills over the side.
What if someone falls in the canal and gets in the turbine?
Well, the turbines turn quite slowly. These are drag designs. In other words, the water pushes them. So in order to make any power, the turbine has to resist the flow of the water. So the turbine turns typically at half the speed of the water flow. So what that means is if you're in the canal and you're floating, you come up to the turbine, you go right over the top of it typically. And it'll just be like a wall that gives way before you. So we expect that these are the safest turbines that could possibly be used in these situations.
What do you do with the power, and how do you connect to it?
Sure. Well, the power can be used from a single turbine, can be used to run, for example, a microgrid on the side of a canal or inside a building. Okay, it can plug right into the panel and you can use it to feed into your existing system. You can run a pump. So now you can irrigate land around the canal, or you can light up a small farm factory or food processing operation. We know of some people interested in lighting up bridges using turbines attached to the bases of the bridges in the river, and they can power lights on the bridge. To interconnect, we're using standard off-the-grid solar modules for anything that has a grid connection, so we can feed into it as an additional source. And then for off-grid systems, we have to have a battery bank that we connect to, and then the battery becomes the load center for the whole local grid.
What about the federal hydropower regulations?
This is a good question because the Federal Energy Regulatory Commission, also known as the FERC, has regulatory authority over all hydropower, no matter how small. If a hydro system is connected to the interstate grid, the feds require that there's a hydropower license, which is a horrific thing to go through and only suitable for big dams typically, or big systems. The FERC does have an exemption for turbines in concrete artificial water channels, which they call conduits. So there is, under federal rule, something called the conduit exemption that allows us to put a turbine in, connect it to the grid, make power, and sell it without having to go through a full federal hydropower license. You still have to apply for the exemption, but it's vastly simpler than it would be dealing with the large-scale application.
How much do the turbines cost?
We're aiming for an installed cost on these machines of between $4,000 to $5,000 per kilowatt. So our 5 kW machine, we'd like to see that priced in the market at around $5,000. $25,000. 5 kilowatts at 5K per kilowatt. And our biggest machine, our 15 kW machine, we're going to price it at around $75,000. So the pricing is, again, designed to be matching the value proposition in the market. In some places, the turbine's worth a lot more, and it'll be priced accordingly. But that'll typically be on a national basis, not within countries.
Have you done any fish testing to see if it hurts fish?
We've not done any testing on fish ourselves. We haven't had the opportunity yet, and it's just a matter of time. Again, we don't really worry about that much because these turbines are in fish-free environments, we expect. Big canals that are lined with concrete. However, fish can get into canals, and people might take a turbine and put it in a river. And so again, the key point is that these designs of turbines, they're slower than the water. They resist the water. To a fish, it looks like a wall. It's not a flashing blade that's going to whack them like a wind turbine would. So we expect that it's a safer design, but again, we'd need to work with fishery agencies to demonstrate that under controlled conditions.
Okay, Burt, we've got time for one more. Is this eligible for production tax credits?
Interestingly, microhydropower is not eligible for production tax credits until it reaches a certain level. So for hydrokinetic turbines like ours, an installation has to generate 150 kilowatts rated output at least before it can get the production tax credit. We don't know why that number of 150 kilowatts was established, and we'd like to see it changed because obviously we'd like the tax credit to work for smaller amounts of power too. So it depends on the size of the project. You could get a tax credit, but it's got to be over the minimum size.
Burt, those are all the questions we have for now, and we'd like to thank you for sharing your time and your insights with us today.
Thanks a lot, everybody, for listening to this presentation. Global Spec puts on great events every year, and we look forward to seeing you again.
Now, before moving on to explore the exhibit hall of this event, please take a moment to click the Take Survey button and let Burt know how he did today. Your feedback helps us improve the quality of our IHS Global Spec events, making them an even better investment of your time. Now, in between sessions, head to the exhibit hall where you'll find manufacturer product reps, engineers, technical specialists, and other professionals waiting to answer your questions. Remember, you can see any of today's presentations during our on-demand period, but exhibitor representatives are only here on the day of the live event, so spend time with them while you can. Please experience our latest innovation, the Knowledge Exchange, offering product demonstrations and our Hot Topic audio briefs. The Knowledge Exchange is also home to our Event Prize Center, so make it a point to visit. Share your thought leadership point of view by speaking at one of our events. You can find the speaker submittal form at our event help desk in the exhibit hall. Well, we'd certainly like to thank you for choosing to spend your day with us, and we'll see you back here in the conference center a little later on.